Good morning, and thank you for attending. This is our monthly seminar series that the New York State Center for Clean Water Technology engages with the public with. This is our outreach to introduce those who are interested in what we're up to at the center. Today, I'm going to give you a snapshot of our next generation of nitrogen removing biofilters. My presentation is relatively short. I only have several slides. The work that Dr. Xinwei Mao, Mr. Siwei Chen, and Dr. Mian Wang are working on is the actual proof of the design concept. And very interesting presentation. So let's see. Okay, so if I'm going to be talking about the next generation, I guess I should bring you up to speed on the first generation. So the first generation is this diagram here. Here's the end view. You see it on the left, and then you have the side view on the right. And it's really quite simple. Septic tank effluent is pumped to roughly 18 inches of sand, and that water flows down through that bed and then enters a bed full of wood chips and sand. The sand is there to prevent compaction of the wood chips over time. The process is easy. There's really no adjustments that can be made. The problem is that the system is fairly large and really can't fit on a quarter-acre lot. You have to have enough area. So when we set out to design the next generation, there were several design criteria we internally talked about. First of all, the system had to have a 30-year service life. It had to be between $15,000 to $20,000 on a commercial basis, meaning that there's others out there that would be in competition with us, so that would drive price. And it would get about 10 milligrams per liter of total nitrogen. This differs a little from our New York State DEC, our own internal goals of under 10 milligrams per liter, but it's going to be about. So the other criteria is not activated sludge. So if you look at the activated sludge systems that are out there now, they're, to be operated properly, they need attention. And we said, you know what, we want to set it and forget it. It has to be easy to operate. And for the most part, I think all activated sludge IA systems out there would do a tremendous job. The problem being that I don't think the labor is there to, quote unquote, babysit the system all the time to get it to its optimum performance. With the system we set out to design, we want to set it and forget it. Technical difficulty. So it had to be substantially passive. I say substantially because we do need a pump, and we do need a small aquarium type blower or air pump. The first generation system, you can really put it together. You can go to Home Depot and buy all the materials. The problem is that it has to be engineered from beginning to start. The elevations have to be decided. With the system we set out, we wanted it to be pre-engineered based on flow, certain model units based on flow. It had to be factory fabricated, meaning that we wanted it to be plug and play. It's assembled at the factory, put on a truck, delivered to the site, offloaded. This would be precast, so it would be offloaded by a machine and set in the ground, connect the in and the out, and there you go, off and running. Hook up the electrical as well, which is minor. It had to be easily maintained, not a lot of issues with the equipment. The equipment has to be hardy and robust. The system in general has to be accessible. All the criteria that I'm accustomed to in municipal wastewater treatment, you know, the operator is the person who has to take care of it and make it run. So we wanted it to be easy. And the major, I believe, criteria was this process flexibility. The name of the process is the FlexTreat Biofilter. It got its name from its flexibility, and it has to be adjustable. Not that it's, you know, you set and forget it for a family, and let's say it's an elderly couple, and they sell to a family with 4 or 5 kids, which is totally different from the loading that the elderly couple had. So it had to be generational. And that's what we mean by process flexibility. So this is the FlexTreat biofilter system. It's a precast structure. The structure is manufactured at a precast shop. The flow comes in from a septic tank. That's this over here. It's filtered in the septic tank, so all the solids remain behind. It flows into an oversized wet well, so which is step 2. So the wet well serves several purposes, really. Let me just go back. Sorry. So the wet well is there. It's flow equalization based. I mean, in municipal treatment, it was where I worked. It was our design practice to always use flow equalization, and the reason for that, it buffers not only the organic load. Think about showers versus restroom facilities versus cooking versus, you know, whatever water usage is there has a separate organic load. Well, the oversized wet well or the influent pump chamber is there to absorb that organic load. The other thing it does, it's a flow equalization basin, so it also eliminates the diurnal fluctuations in the flow. People waking up in the morning, getting dressed, having breakfast, and going to work, at least in pre-COVID days. And, you know, they come home and all that leads to this diurnal fluctuation. Well, what if we took that diurnal fluctuation and flow paced it throughout the entire day? One flow rate, a flow rate that would not shock load the system, but would be constant throughout a 24-hour period. And the use of a positive displacement pump with variable speed drives and all that is part of the design. Nowadays, electronics are very, very cheap. Couple $100 buys you a system that back 20 years ago was $2,000 or $3,000, maybe even more. The other thing this wet well does is for pre-aeration. It jump starts the nitrification process, the conversion of ammonia to nitrates. So we want to aerate it. The next step is through a filter bed. This is the equivalent to the sand filter of the first generation. So this initially the prototype will be starting out with sand, then we'll be moving on to other types of media, synthetic media, biochar, different proportions, all in the hopes of decreasing the size of the bed. And we're now performing experiments that conclusively demonstrate that. But the work that you'll be seeing that Siwei worked on and Mian and Xinwei, the system is based on a sand filter system. So the flow then from the sand filter it's split. Some of the flow goes to item work 4, the circle 4 there, which is a polishing filter. All it does is there's a leaching pool with a tank in the leaching pool, and it has wood chips in it. So it polishes the nitrates. The major conversion you see goes to circle number 5, which we're calling an oxic compartment. So what we're learning is the sand filter, has plenty of DO in it, 6-7 milligrams per liter. Well, the next step in the process is anoxic. So if we don't get close to near DO, we have DO carrying into the anoxic phase, which is just going to retard the conversion of nitrates to nitrogen gas. So we hydraulically send it to an anoxic compartment, which dissipates the oxygen. And then from there, it flows. So these pipes here, these are all throttling valves to adjust flow rate. The prototype is built like that. The commercial version will not have those types of things. This is for experimenting at the research facility. So the flow comes into the anoxic compartment, fills up. The hydraulic gray line, there's a slot in the wall that holds the, that's the water level. This water level in the wood chips are controlled by an elevation in the wet well. So the flow comes through, down. This has a certain detention time and flows into here as a recycle flow. So 6 is the wood chip portion of the design, and that adds carbon. So we've taken out all the carbon in the nitrification step. We need a source of carbon, and that's where the wood chips come in, natural carbon. The flow then is into the aeration tank. And this recycle rate is one of the things that we adjust based on the organic and hydraulic load of the system. So right now, we're working with Roman Stone Construction. They're a precast house in Bayshore. And we have a research agreement with them as a collaborator. And we're now designing the shop drawing for the prototype. So the dimensions are roughly 5 feet wide, 4'8", 13'4". This is all with internal walls, precast concrete walls. And then an overall height of 6 foot 8 inches. So that's the Flex Treat biofilter. So the way this project got started is back in March of 2018 up until December of 2019, we developed the design criteria, and we also developed the process concept. So right now we have a provisional patent, and I want to do a shout out to Donna Tuminello and James Martino, who have been absolutely fantastic. They work for the Office of Technology Licensing. That's what's great about working for an academic institution. There's departments here that help to bring ideas to reality, and part of that obviously is the patent process. Now we're undertaking, since June of 2019, we've been proving the concept, and that's the second part of this conversational. And Siwei, who's a PhD candidate, will be presenting that. The prototype design, since September of this year, we've been working with Tom Montalbine and Cheryl Worth. I know they're on the call today. Thanks, guys, for joining. They've been absolutely fantastic. And they're investing. They've agreed to build the prototype for no charge. So we then move on to the prototype construction installation. That's scheduled for the first quarter of 2021. Now then we have to, once it's in the ground, we're actually putting this prototype in the ground at our wastewater research and innovation facility. Luckily, we have that. And we'll be doing performance evaluation and testing on the full-scale prototype. That should go to 2022. And then finally, we enter into the Article 19 process, which is now would take us 5 years to go from experimental to general use. So luckily, we do have a wastewater research and innovation facility. We broke grounded in 2018. We completed in July of 2019. It's now fully functioning. We have columns. The columns in photo 3 show where the testing has been done on the prototype, on the column testing for our next gen system. You see they're just trailers in photo 1. We have another trailer that's for test tube size testing, small columns. And in photo 6 shows the area just north of the trailer, and that's where our prototype would be installed. This site is an existing pump station owned by Suffolk County DPW. So we take a side stream flow from the pump station, and we pass it through via the piping and the tanks. We pass it through our column size systems. We monitor the flow, we monitor the constituents, we monitor the concentrations, and it's then returned back to the Suffolk County pump station. The flow never goes into the ground at that point. So I'm through with my portion. I want to thank you. If you have any questions for me or for Siwei, just send them to my attention and I'll try to get them answered for you. So with that, Siwei, I think you should take over the screen.
Okay. Can you stop
Yeah.
sharing?
Yeah.
Okay.
Sorry.
That's fine. Okay. Can you see my screen now?
Yep.
Okay. So my name is Siwei Chen, and I am a PhD student from the Civil Engineering Department of Stony Brook University. So thanks, Frank, for introducing the overall picture of the flex-treat biofilter development. So I will provide more details about our pilot-scale flex-treat biofilter system. So firstly, I want to introduce some background for our flex-treat biofilter system. So in Long Island area, over 70% of the households rely on the on-site wastewater treatment system to treat their sewage. But for most of those on-site wastewater treatment systems, they're not designed to remove the nitrogen. And if we release the nitrogen directly into the receiving water body, it will cause the eutrophication, which can impair our drinking water quality and the water ecosystem balance. Here is the configuration for the septic tank soil absorption system, which is the most commonly used conventional on-site wastewater treatment system. It comprises a septic tank and followed by a soil treatment unit. The wastewater produced from the single home will firstly flow into a septic tank, and the septic tank can collect and partially decompose the solid in the wastewater. Then the effluent from the septic tank will be distributed by the leach field or a drain field to the soil treatment unit. The soil treatment unit can be served as a nature sand filter to provide the secondary treatment for the septic tank effluent. If this kind of system can be installed and maintained correctly, it can achieve efficient total suspended solid, biochemical oxygen demand, and pathogen removal. And you don't need to pay a lot of money on installing this kind of system, and it doesn't need a lot of maintenance. But as I mentioned, it's a conventional on-site wastewater treatment system. It cannot effectively remove the nitrogen. Also, not all the septic tank soil absorption system can be installed correctly. Nearly 1/3 of the soil in the North America may not meet the modern drain field design requirement. So we need a new design for the on-site wastewater treatment system to achieve very good nitrogen removal performance. That's why we have our current nitrogen removing biofilter system. Our current NRB system comprises an upper nitrification sand layer and a lower denitrification sand and lignocellulose layer. In the nitrification sand layer, the nitrification can convert the ammonium to nitrate, and the BOD decomposition process can remove the BOD from the septic tank effluent. And the nature aeration can provide enough oxygen for the nitrification and the BOD decomposition processes. In the denitrification sand and lignocellulose layer, the denitrification can convert the nitrate to nitrogen gas, and the lignocellulose material, such as the wood chip and the sawdust, can be served as a carbon source for the denitrification process. Our current NRB system is proved to achieve the low effluent TM concentration, and it doesn't need a lot of maintenance. But the biggest problem for our current NRB system is the footprint. Our current NRB system requires a very high footprint. The high footprint can cause a high construction cost, which is not affordable for most of the families. So we need to upgrade the design for the current nitrogen removing biofilter system to achieve both the efficient nitrogen removal performance and the low footprint. That's why we have our flex-treat biofilter system. Our flex-treat biofilter system comprises an aeration tank, a nitrification column, an intermediate denitrification column, and a final denitrification column. The septic tank effluent will flow into the aeration tank firstly and mix with the recirculated intermediate denitrified effluent from the intermediate denitrification column. The air pump can aerate the mixed flow in the aeration tank before it enters into the nitrification column. The nitrification column is filled with sand and is operated as a downflow reactor. The effluent from the nitrification column will be distributed into an intermediate denitrification column and a final denitrification column. For both of the intermediate and final denitrification, they are filled with 1% of the wood chip, and they are operated as an upflow reactor. The effluent from the intermediate denitrification column will be recycled back to the aeration tank, and the effluent from the final denitrification column will be discharged directly. Our flex-treat biofilter system has some unique features. Firstly, it's a continuous flow reactor. The continuous flow can keep a constant water content at the surface of the filtration media, which is in favor of the growth of the microorganism. And it has an internal recycle pattern, which can increase the internal detention time of the contaminant. And it has a pre-aeration system, which can provide enough oxygen and for the nitrification and BOD degradation in the nitrification columns. This table compares the flex-treat biofilter system with some similar on-site wastewater treatment systems. The first one is the recirculating sand filter. The recirculating sand filter is a dosing flow reactor, and it utilizes a pre-denitrification treatment configuration, which means that it recycles the nitrified effluent from the sand filter back to recirculation tank or the septic tank. And the recirculation system have the recirculating sand filter can achieve a very small footprint. The recirculating sand filter system shows a very great BOD removal performance, but it cannot achieve very good nitrogen removal performance. Also, for the recirculating sand filter, it requires a frequent maintenance. A weekly maintenance is suggested by the EPA for the recirculating sand filter. The second system is our current NRB system. The current NRB system is also operated as a dosing flow reactor, and it doesn't have any recirculation system, and that makes our current NRB system has a very high footprint. Our current NRB system can achieve both high BOD and nitrogen removal performance, and it doesn't need a lot of maintenance. Our flex-treat biofilter system is operated as a continuous flow reactor, and it recycled the denitrified effluent back to a very small pump tank. So that helps the flex-treat biofilter system can achieve very small footprint. Also, the flex-treat biofilter system can achieve both high COD and nitrogen removal performance, and it doesn't need a lot of maintenance for the flex-treat biofilter system. For our flex-treat biofilter system, we have some research questions. Firstly, can the flex-treat biofilter system achieve target nitrogen concentration, which is 10 mg per liter in effluent with proposed flow pattern? Secondly, how does the operational conditions, such as the hydraulic loading rate and recycle ratio, affect the extent of nitrification and the subsequent denitrification performance? The operational strategy for the flex-treat biofilter is, firstly, we started the system with a hydraulic loading rate of 0.75 gallons per day per square foot, which is same as our current NRB system, and a recycle ratio of 2. Then we will stepwise increase the hydraulic loading to challenge the current recycle ratio until the incomplete nitrification or denitrification is observed. Finally, we will adjust other operational parameters such as the recycle ratio and the pre-aeration rate to achieve the optimum treatment performance. This slide shows the different operational stage for flex-treat biofilter system. At stage 1, we only started the nitrification subunit, and we use the tap water to simulate the recycle flow. And also at the stage 1, we started the nitrification subunit with a hydraulic loading rate of 0.75 gallons per day per square foot and the recycle ratio of 2. At stage 2A, we started the denitrification subunit, and we still use the tap water to simulate the recycle flow. For all of the denitrified effluent, they are discharged directly. And at the stage 2B, we started the entire system, which means that we use the intermediate denitrified effluent as the recycle flow. And at the stage 3A, we increase the hydraulic loading rate to 2 gallons per day per square foot, and we keep the recycle ratio same as 2. At the stage 3B, we tested the performance of the flex-treat biofilter system to treat the wastewater containing high concentration of the TN. We increased the influent TN concentration to around 70 mg per liter by mixing the septic tank effluent with a synthetic ammonia stock solution. And at stage 3C, we further challenged the system performance with higher influent TN concentration, which is around 100 mg per liter. So for the following slide, I will discuss the result for the stage 2B, stage 3A, stage 3B, and stage 3C. Next, I will introduce the treatment performance of the flex-treat biofilter system. Firstly, I will introduce how do we perform the water sampling from the flex-treat biofilter system. Then I will discuss the result of the total nitrogen, the chemical oxygen demand, alkalinity, dissolved oxygen, and the different nitrogen species at all the treatment stages. To monitor the treatment performance of the flex-treat biofilter system, we collected the septic tank effluent, pump tank effluent, nitrified effluent, if intermediate denitrified effluent and final denitrified effluent from the flag treated biofilter system regularly around every 3 to 5 days for the water characteristic analysis. This slide shows the TN concentration in the flag treated biofilter system. The x-axis is the operational days and y-axis is the TN concentration. The black line is the septic tank effluent. The red line is a pump tank effluent. The blue line is the nitrified effluent, and the green line is the intermediate denitrified effluent, and the purple line is the final effluent. At the middle of the stage 2B, we shut off the entire system for around 2 weeks to test the performance of the flag treated biofilter system to get recovered from a long-term idle period. And at the early stage of the stage 3A, our lab was closed for around 2 months due to the pandemic of the COVID-19. So during that time period, there's no sampling, but we still normally operate and maintain the flag treated biofilter during that time period. The flag treated biofilter system shows very great TN removal performance at all treatment stages. At stage 2B, with a hydraulic loading rate of 0.75 gallons per day per square foot, almost all the TN can be removed by the flag treated biofilter system. The final effluent only contains around 0 milligram per liter of the TN. And the TN removal performance of the flag treated biofilter system can get quickly recovered from the long-term idle period. It can achieve very low concentration of the TN in the final effluent, even at the first day we restarted the system from a long-term idle period. At stage 3A, the TN concentration in the final effluent increased to around 2 milligram per liter. That's because the increasing, the higher hydraulic loading rate reduced the HRT in the system, which shortened the reaction time between the reaction time for the nitrification and the denitrification processes. Also, the higher hydraulic loading rate increased the TN loading for the entire system, which brings more treatment pressure for the entire system. At stage 3B, we increased the TN concentration, influent TN concentration to around 65 milligram per liter. And we also further increase the TN loading for the entire system and bring more extra treatment pressure for the system. So the final effluent TN concentration increased to around 5 milligram per liter. And at stage 3C, we've further increased the influent TN concentration to around 95 milligram per liter. And our final effluent contains around 10 milligram per liter of nitrogen. So the flag treated biofilter can also achieve our target effluent TN concentration under such a very high TN concentration. This slide shows the COD concentration in the flag treated biofilter system. The x-axis is the operational days and the y-axis is the COD concentration. Here we can find the flag treated biofilter system can also achieve very efficient COD removal performance. Also, the treatment performance of the COD can get quick recovered from the idle period. It can achieve very low concentration of COD in the final effluent. After a few days, we started the system from the long-term idle period. This slide shows the alkalinity concentration in the flag treated biofilter system. X-axis is the operational days, and y-axis is the alkalinity concentration. Here, at the stage 2B and the stage 3A, enough alkalinity can be provided by the mixed flow containing the septic tank effluent and the intermediate denitrified effluent to maintain the reasonable pH range in the nitrification columns for the denitrification and the BOD degradation processes. And at the first week of the stage 3B, low alkalinity concentration are observed in the nitrified effluent, which is here, which is the blue line. And that may be caused by So at the stage 3B, we increase the influent TN concentration by mixing the septic tank effluent with a synthetic ammonium stock solution. At the first week of the stage 3B, the ammonium stock solution only contains ammonium. So we didn't add any alkalinity into the solution. So the alkalinity in the pump tank effluent is not sufficient to be consumed by the nitrification process in the nitrification columns. And that also caused a low pH value observed in the nitrified effluent. And also inadequate nitrification performance. So after the first week of the stage 3B, we add the external alkalinity into the ammonium stock solution as the ratio of the 7:1 with the concentration of the alkalinity to the ammonium. Then we can find that the alkalinity concentration in the nitrified effluent return back gradually to a reasonable range, and our nitrification performance also got recovered. This slide shows the DO concentration in the flex-treated biofilter system. The x-axis is the operational days, and the y-axis is the DO concentration. So here I want to mention that, so our air pump was off for all of the treatment stages, but we can still observe a very high concentration of the DO in the nitrified effluent, which may indicate that the nature aeration can provide enough oxygen for the nitrification and the BOD degradation processes. Also, the high DO in the nitrified effluent caused the high DO observed in the denitrified effluent. So even we can observe the sufficient denitrification process in all treatment stages. So the denitrification process may occur in the anoxic zone created at the surface of the wood chip media. So in this slide, we compare the different nitrogen species at all treatment stages. The x-axis is represent the septic tank effluent, pump tank effluent, nitrified effluent, and final effluent at different treatment stages. And the y-axis represents nitrogen concentration. The black bar shows the ammonium concentration. The white bar shows the NOx concentration, and the gray bar shows the dissolved organic nitrogen concentration. So as we can see in this figure, so the final effluent at all treatment stages contains very low concentration of the ammonium and dissolved organic nitrogen. So only the significant increment of the NOx can be observed when we increase the hydraulic loading rate or we increase influent TN concentration. That may indicate that the denitrification process is the limiting step for the nitrogen removal in the flex-treated biofilter system. So to better understand the nitrogen transformation level, the relationship between the nitrogen transformation level and the functional microbial species, and also to optimize the mathematical model to predict the performance and the longevity of the flex-treated biofilter, we also investigate the microbial abundance and distribution in the flex-treated biofilter system. We collected the sand samples from 4 different layers of the nitrification column, and we also collected the wood chip samples from 3 different layers of denitrification columns. Here, I want to thank Dr. Mian Wang for helping us to conduct the microbial analysis. In this project, we mainly use the quantitative real-time PCR, also called qPCR, to quantify the microorganism in the flex-treated biofilter system. qPCR is a PCR-based technology which can amplify and quantify the DNA in real time. It has been widely used in the environmental microbial analysis to detect and quantify the microorganism we are interested in. Also, it can help us to have a better understand the complexity of the micro community in the wastewater treatment system. So for the flex-treated biofilter system, we firstly collect the sample. Then we extract the DNA or RNA from the solid samples. And then we establish the selectively primer for the target functional genes. Then finally, by using the primer, we can quantify our target functional gene by using the qPCR assays. These two figures shows the nitrogen pathway in the flex-treated biofilter system. The first one is the nitrification pathway. Nitrification process is a two-step biological process containing nitritation and nitratation, which are performed by the ammonium oxidizing bacteria or archaea and the nitrite oxidizing bacteria, respectively. And the AMOA function gene in AOA or AOB is the most commonly used biomarkers to investigate the nitrification process. And for the denitrification pathway, the reduction of the nitrite to nitric oxide is catalyzed by two kind of equivalently functionalized reductase. The first one is the copper-containing enzyme, which is encoded as a NERK, and the second one is the cytochrome enzyme, which is encoded as a NERS. And the reduction of the nitrous oxide to the nitrogen gas is catalyzed by the nitrous oxide reductase, which is encoded as the NOS-Z. So the NERK and NOS-Z functional genes are most commonly used functional biomarkers to investigate the denitrification pathway. So here, this slide shows the microbial distribution in the nitrification column. The x-axis is the different column layer, and the y-axis is the log gene copy number per gram, and the red dashed line represent the concentration of different functional genes in the blank sand samples. And here, the total biomass of the bacteria was measured by the quantity of the 16S rRNA. Here we can find all the functional genes containing the 16S rRNA, AMOA AOA, and AMOA AOB shows the similar distribution pattern in the nitrification column. The top layer of the nitrification column containing the highest concentration of the 16S RNA, AMOA AOA, and AMOA AOB, and the concentration for those functional genes decreased with the depth of the nitrification column. This slide shows the microbial distribution in the denitrification columns. The x-axis is the column layer, and the y-axis is the log gene copy number per gram. And the blue dashed line represents the concentration of functional genes in the blank wood chip samples. The red bar represents the intermediate denitrification column, and the orange bar represents the final denitrification column. So all the functional genes, including the 16S rRNA, NERS, NERK, and NOS-Z, shows different distribution pattern in the denitrification columns compared with the nitrification columns. All of the functional genes are evenly distributed in the denitrification columns. I think that may be caused by the flow pattern, the different flow pattern in the nitrification and denitrification columns. The nitrification column is operated as a downflow unsaturated flow pattern, and the denitrification column is operated as an upflow saturated flow pattern. So here is a summary for our treatment performance side. So firstly, the flex-treated biofilter system shows efficient COD and nitrogen removal performance with proposed flow pattern at all stages. Secondly, the treatment performance of flex-treated biofilter is able to quickly recover from long-term idle period. System shutdown doesn't pose significant impact on the treatment performance of the flex-treated biofilter system. Thirdly, the natural aeration can supply the adequate oxygen for the nitrification and the COD degradation processes at all stages. And finally, the alkalinity plays an important role in maintaining the optimal pH range for the nitrification process. Here are the summary for our microbial part. Firstly, the abundance of the 16S RNA, AMOA-LA, and AMOA-LB genes decreased with depth in the nitrification columns, and all target genes were evenly distributed in the intermediate and the final denitrification columns. We quantified the functional genes in the flex-treated biofilters at the stage 2B and the stage 3B. So both stages shows a similar distribution patterns of the functional genes, but the overall quantities of 16S RNA and functional genes at the stage 3B are 1 to 3 orders of the magnitude higher than those in the stage 2B. So here I want to thank Mr. Frank Russo, Dr. Xinwei Mao, Dr. Mian Wang, and Dr. Stuart Wall for providing a lot of help on this project. And I also want to thank everyone in the New York State Center for the Clean Water Technologies. And I also want to thank the New York State Department of Environmental Conservation for funding this project. Thanks very much.